Hello everyone, and welcome to today's webinar, Intel Compilers Overview, Scalable Performance for Intel Processors. Our presenter today is Igor Vorobtsov, a Senior Technical Consulting Engineer in the Developer Products Division here at Intel. During this presentation, please send in any questions you may have, and we will get to as many of them as we can during the Q&A session at the end of the presentation. We now turn the time over to Igor.
Hello everyone. Hope today will be a very nice talk on our Intel compiler features. So let's start. Today we are going to talk about why should we use the Intel compilers and briefly go over the most important features of the Intel compiler you may use in order to get the best performance of your hardware. Especially we will talk in more details about high-level optimizations, optimization reports, IPO, which is inter-procedural optimization, auto-vectorization, which is a major part of our compiler and gives the best benefit for you, as well as dynamic profile-guided optimization and auto-parallelization. So first question you may have in your mind is why should I really use Intel compiler? And the main reason to use it is performance. So a simple way to boost performance of your application is just simply recompile your code using our compiler, and it will produce a highly optimized code that can run significantly faster by taking advantage of increasing core count or vector registers. And today we will talk in more details on the basic compiler features you may use to boost performance of your application. Here you can find some general compiler features highlighted. So we add the support for the latest standards incrementally in successive compiler versions. So let's say in 18.0 compiler we supported C11, C++14, and also have a full OpenMP 4.0 standard and almost all features from 4.5 standard. In the latest beta version compiler, which is 19.0, the only missing feature from OpenMP 4.5, which is user-defined reductions, is also supported. So now we can state that OpenMP 4.5 is fully supported as well. Note that we do have binary compatibility with GCC compiler, which comes from using GCC runtime libraries. So you can mix Intel compiled code with objects or libraries compiled with GCC with no issues. There are many advanced optimization available, and in the next slides we are going to talk about it. One of the most important optimizations are high-level optimization, which exploit the properties of source code constructs, for example, loops or arrays in your application developed in high-level programming language in C, C++, or Fortran. So there are three different levels of HLO you may actually set. In order to disable all optimization, you need to set the optimization level 0. So this option may set other options as well, for example, -G for debugging. So you need to be very careful and note that setting some options explicitly may implicitly set some other options as well. So for example, let's specifying -G explicitly generate full debugging information in the object file and also disables all the optimization. So implicitly setting -0 unless you explicitly specify -02. So then the next level of optimization the compiler may do with your code is 01, and this option enables optimizations for speed and disables some optimization that increase code size and affect speed. So we may suggest to use this option if you want to have a nice performance but still care about the code size. To limit code size, this option enables global optimization and disables inlining of some intrinsics. It is important to highlight that we will talk about auto-vectorization later, but you need to know that it is actually disabled with O1 level, and it is the main difference between O1 and O2 level, which is the next optimization level. There, auto-vectorization is enabled by default, and it can give you a really great performance gain. So auto-vectorization is a major feature of our compiler, and in most cases, this is the part of the compiler giving you most benefit. Note that this option O2 also enables many optimizations like intra-file, inter-procedural optimization, and it includes inlining, constant propagation, dead static function elimination, and so on. Next, the highest optimization level, O3, provides the best chance for performing loop transformations to optimize memory accesses. So, for example, with O3, if we compare it with O2, the compiler is able to do loop fusion, cache blocking, block control and jam, and more aggressive optimization. Note that with O3 option, the compiler performs more aggressive data dependency analysis, which may result in longer compilation time. And you need to understand that usually if you are going to have a best performance for your application, then it's always a trade-off between the compilation time and the actual performance gain you are getting. Optimization report is a powerful feature allowing you to understand what was the compiler doing with your code. And it is important for us to understand what actually compiler did with our code, which optimizations were applied or not applied, and understand the root cause of this. So you may tell the compiler to generate an optimization report using special dedicated option, which is QOptReport. If option is set, then the compiler generates a collection of optimization report files, one per object by default. If you prefer another form of output, you can still specify option QOptReport file and set the optimization report file explicitly. There are different levels of details available from 1 to 5. So a higher number, more details you are getting from the compiler on what it actually did. When optimization reporting is enabled, by default is QOptReport phase all, showing reports from all optimization phases. However, you may control it by using QOptReport phase option. So, for example, you can set QOptReport phase to vectorization in order to get only the optimizations from the vectorizer which you applied for your code. And later we will see some nice examples on this. Note that in the past we have a other option which was called OptReport, and now it is actually deprecated, and we had a Vec report as well. So now it is all replaced with only one option, OptReport, and you can control the phase explicitly. So Vec report is replaced with the option OptReport phase Vec now. Now we will talk about one more really interesting optimization, which is called inter-procedural optimization. It is an automatic two-step process that allows the compiler to analyze your code and get the benefit from the specific optimizations. So the compiler may apply many different optimizations like function inlining, constant propagation, etc. But the idea is that with IPO, the compiler analyzing and optimizing across function or source file boundaries. As we already talked, with auto-optimization level, we are getting quite large number of different optimizations the compiler may apply. But with auto optimization level, the compiler analyzes each file individually and produces object files for each source file. For example, if some function is called in one source file but is implemented in the other file, then the compiler will be not able to inline it. If source file is compiled with IPO, the compiler stores an intermediate representation, IR, of the source code in a mock object file. And when you link with the IPO compiler option, the compiler is invoked a final time. So that's why it is called two-step compilation. First time, and then during the linkage time, it is invoked again. In this case, the compiler performs IPO across all mock object files. Using extra information, the compiler performs optimization across functions and procedures in different source files. It may cause increase of build time and binary size, of course, but the performance benefit may be quite significant. So in this slide illustrates the idea of optimizations across functions and procedures. Here you can see that the IPO analysis benefits function inlining and many other optimization phases in the compiler. Look at it like this. The IPO analysis provides information to other optimization passes so that they in turn can do a better job. So more information the compiler getting during compilation time, the better performance you're finally getting. Note that with IP option, not IPO, but IP, the analysis is limited to occur within each source file. And with IPO, the analysis spans all of your source files. In other words, code generation in module A can be affected by what is happening in module B. Intel compiler comes with highly optimized math libraries, and here I'm not talking about MKL, but I'm more talking about library function, math library functions included in the compiler itself, like libimf for scalar versions or libsvml for vector or scalar. Note that driver links these libraries by default, so you don't need to specify it explicitly. And it is better to avoid explicit libm linkage to avoid slower libm functions usage. We have many new features introduced in the latest compiler version. For example, in the latest 18.0 version, we introduced the scalar implementation for libsvml functions. Actually, libsvml is a short vector math library which is expected to be only for having only vectorized implementation of the functions. However, for result reproducibility, our developers also introduced the scalar versions. So now vector and scalar versions produces reproducible results, which means that with the latest compiler, even with a precise floating model, you can still use the vectorized math functions, and more loops can be vectorized finally. Before talking about vectorization itself, let's take a look on what is SIMD. So SIMD is a single instruction multiple data, and it is actually a class of parallel computers in Flint's taxonomy, which describes computers with multiple processing elements that perform the same operation on multiple data points. Such machines explode so-called data-level parallelism. As far as you know, there is also a task-level parallelism, and we will talk about it later, but the next slides we'll talk about data level parallelism and vectorization. Note that CMD is applicable for loops, and here you can see an example of simple loop. The idea is that we can perform an addition operation for multiple elements of arrays. However, CMD instructions may still work in a scalar mode as well. For example, the instruction v_add_ss, you need to care about the last letters in these instructions, which are ss, is a scalar instruction producing one result. So first S here means scalar. v_add_ps is an example of packed CMD instructions, which works in a vector mode, and P here means packed. So when packed CMD instructions are generated, the loop is said to be vectorized or auto-vectorized if it is done. So now we are ready to talk about vectorization in more details. Vectorization itself is the generation of loops using packed CMD instructions, as was already stated. There are different ways to vectorize the code. We may use the compiler auto-vectorization feature, which is enabled by default with O2 optimization level, so you don't need to specify it explicitly. By the way, O2 level is enabled by default as well, so if you invoke the compiler by using ICC command, then O2 is set implicitly and vectorization is enabled as well. But the only concern is that by default a compiler is too conservative and will be not able to vectorize loops in many cases where it needs to know some additional information. So usually the reason why auto-vectorization doesn't work is lack of some information for the compiler. Note that in this way, in auto-vectorization, the compiler is responsible for correctness, and in case it is not clear is it safe to vectorize or not, then it may avoid vectorization of the loop. Next, with assisted vectorization, we may pass some additional hints to the compiler to help vectorize the specific loop. Note that in this case, the compiler is still responsible for correctness. And next, final level of control over compiler vectorization is to use explicit vectorization model, which were introduced with OpenMP 4.0 pragmas. In this case, user is responsible for correctness, so the compiler doesn't check anymore if it is safe to vectorize the code or not. So you overriding the compiler heuristic. Use it when the compiler is unable to auto-vectorize or when you want control over how a loop gets vectorized. Note that there are also some low-level options to vectorize your code. For example, you can use the assembler or write using intrinsic functions. But in this case, the solution is not so portable. Let's say you have created a version of your code with intrinsic functions, but once the new hardware is available, you need to rewrite your code. Moreover, you need to support and maintain this code as well, which can be quite tricky. So we recommend to use a compiler to do this. You may prefer auto-vectorization, assisted vectorization, or explicit vectorization. And today we will more talk about auto-vectorization with the compiler options. And on this slide you can see that you can control the instruction sets and optimization which the compiler may do with your code. So by default, Intel compiler using an SSE instructions in order to auto-vectorize your code. Note that this is not the latest available instruction set, and the latest hardware actually support AVX512, for example. So if you know that you will run your code on some latest hardware, you need to explicitly set the instruction set and optimization the compiler may use to produce a final code. Let's say for Skylake server, you may say -x core AVX512, and in this case, the Intel compiler will generate AVX512 instructions for Skylake server, getting benefit of long registers and generating highly efficient code with compress expand instructions or using conflict detections and so on. Note that in this case, if you run the application on the non-Intel processor, then the runtime error will occur. In case you don't want to hit this situation, you may compile your code with -m option, which actually produce still highly optimized code, but not specific for microarchitecture. So in this case, the code may be not so fast, a bit less efficient, but it still allow you to run on non-Intel processors as well. The option for convenience was introduced some versions ago. It's called -x host, which allows you to compile on your host processor, which means if you are going to run the application on the same system where you develop your application and compile it, then the compiler will use the highest instruction set available on your current host processor. Dependencies is the main reason why the compiler cannot perform an auto-vectorization. So vectorization is usually safe only if one CM delay doesn't depend on the result of another. Note that only dependencies on the result of a preceding loop iteration prevent vectorization. So let's take a look on this example, which is called read after write dependency. So dependencies on an iteration more than n iteration early, where n is the vector length, are okay, but not going into that here. Right after read dependency, where a variable is updated in a later iteration after original value was used, in an early iteration don't prevent vectorization, but do prevent auto-parallelization. So here, in this particular example, you can see that for the I value set to 2 for the second iteration, the fourth element of the array A, which is A4, depends on the result of a 0 iteration, which is the second element of array A. So this kind of dependency is called loop-carried vector or flow dependencies. And if we are going to compute both these values in the same CMD instructions, then the result for a second element of array is not yet available when the fourth element of array A is computed. So in this case, the original value for the second element will be used, and the result for the fourth element will be incorrect. In this case, the compiler is not going to auto-vectorize the loop, and you shouldn't force it even using explicit vectorization, because it's just incorrect. Note that the compiler must be conservative, as already mentioned earlier. In this case, you can help the compiler using spatial pragmas, and this is called assisted vectorization. Actually, not all potential dependencies are real. If we will take a look on this particular example, you will see that there are two pointers passed inside the function scale, and the compiler assumes that these pointers pointers might be aliased. So what you can do is to actually help the compiler by saying, please be sure that there is no aliasing of function arguments. And you can do it by compiling with f-argument no alias option. There are also two other options available here. One is to use the restrict keyword, which says that this pointer cannot alias with any other inside these functions. Or you can also use a pragma ifdep, which is a Intel compiler specific pragma, which is saying ignore vector dependencies before the loop. However, if a compiler is sure that there are dependencies between some data elements, then the compiler will avoid vectorization. That's why the compiler heuristic is still used, and it is quite safe in comparison with the explicit vectorization. By the way, the compiler can do a loop multiversioning in this case, which means that it can generate a vectorized version of this loop and non-vectorized version and check if the data dependency is real during the runtime. If it's not, then it is safe to perform and execute the code which is vectorized. And here you can see the guidelines for writing vectorizable code. So first of all, the simplest the for loop, the better for the compiler. Which means, for example, the trip count should be known at loop entry. It may be a case that the pointer is passed to a function and we are using a trip count using this pointer. And in this case, it is not known at loop entry. And on each iteration, in according with the C standard, we need to check the real value of this variable. Sure, you need to avoid dependencies on an earlier loop iteration, and in this case, you need to avoid read after write dependencies, while write after read is still okay for vectorization. Note that usually the compiler is not able to vectorize the loop with a function calls inside, unless this function call is inlined or it is a simple math functions and the vectorized version is available with the compiler from the SVML library. Branches that can be treated as math assignments is the other case which may prevent vectorization as well. One more interesting thing here is that it is better to prefer arrays to use of pointers. Note that these are not necessarily absolute requirements, but usually they make auto-vectorization much more likely or efficient. The compiler also has an efficiency heuristic inside, and sometimes it may not vectorize the code because for the compiler it looks like it is not efficient to do it. It happens quite often with the loops with a non-unit stride access, so it is much better if you have unit stride access in order to get a better performance. Minimize indirect addressing as well, because in this case we are jumping through our memory in a random way, which is not really good for performance as well. And the last but not least is to align your data, because the alignment may also impact the performance in case the 2 cache lines will be used instead of 1. I already talked about it a bit, but there are many different reasons the loop may not be vectorized, and the idea is to go to optimization reports, and we will do it soon, in order to double check why the compiler was not able to auto-vectorize this or that loop. But quite common, the reason is that the trip count was not known, or the dependency actually exists, or it doesn't exist in reality, but the compiler assumed it because it doesn't know too much about your code. Really often cases, a function call is used inside the loop. Compiler doesn't expect performance gain in some cases, and efficiency heuristic is still really important, but you can still override it using a special pragma, which is called pragma vector always, which says, please ignore the efficiency heuristic for this specific loop. For a case when the trip count is really low, then it doesn't make any sense to vectorize the loop, because the performance will be not so high in comparison with the serial execution of this loop, or maybe in some cases even worse. So for low trip count, the compiler usually doesn't auto-vectorize it. Complex control flow also is an often root cause for the compiler to not vectorize the code. So please avoid these control flows with large switch statements or goto statements and many nested if statements as well. Note that you can have a collapse loops, right? So in this case, if you have nested loops like with outer loop or inner loop, the compiler are usually able to vectorize the inner loop but not the outer loop. So with the latest version of the compiler, it now can vectorize outer loop as well, but usually you need to use the special OpenMP directives in order to auto-vectorize outer loop as well. Here is a nice example of optimization report you can use in order to understand what is happening. On the right-hand side, you can see quite simple code with a function foo, and we are compiling the code using -x common AVX512 option, which means we would like to target Skylake server or KNL architecture with a QOpt-report function. In this case, we are controlling the opt-report phase to show us which optimizations the compiler applied for loops and information from vectorizer as well. So in this case, for the file foo.c, the compiler will generate a file foo.opt-rpt summarizing which optimizations the compiler performed. And here we set the level of details to 3, to the middle, because it starts from 0 and no report, and the more detailed level is 5, which is the maximum. So here is how the optimization report actually looks like. From the report, you can obviously see that this specific loop was multi-versioned, which means in this case the compiler generated one version which is vectorized, and you can see the statement loop was vectorized here, and the other loop, multi-versioned version 2, which is not vectorized for the reason that there is a data dependency. So during runtime for this specific loop, we will understand if the dependency exists in reality, and then execute vectorized or non-vectorized code depending on this. However, we can help the compiler by adding an option f argument no aliasing. So in this case, we are saying to the compiler that it is expected that all pointers which are passed as an argument for a function are not aliasing. And in this specific case, it is safe for a compiler to do a vectorization. So here you can see that no versioning is done for dependency because they used this option. By the way, you can also look at the compiler performance estimate for this loop. It is almost 10x speed up from vectorization, which is a significant benefit. However, there is a message about type converse here, and this may introduce overhead. Let's look at the source code. STH and theta are single precision floats, and literal constant 3.14, which is a pin number, is double precision in C language. So adding this to theta makes the argument of sinus function double precision, which in turn causes a double precision version of sinus to be called. It's unlikely that a double precision call to sinus is needed when the result will immediately be converted back to single precision. So we can easily fix this. It will be sufficient here just to replace the constant 3.14 by 3.14f at the end. But it is safer to convert sinus to sinus f as well, so that the single precision call is explicit. So we did this modification to our code, and you can see that there are no more messages about type conversions here, and the estimated speed up from vectorization almost doubled. So you can also take a look on the assembly code and see that for each vectorized iteration, 2 calls to vectorized sinus functions, which are SVML sign, were generated by the compiler. So in this case, vectorized short vector math library functions were used. One more interesting optimization which you can use in our compiler is called profile-guided optimization. In comparison with IPO, which was static, profile-guided optimization is a dynamic kind of optimization. So it will be great if a compiler may know some runtime data. In this case, it can apply even more different optimization to our code, because now it knows which path of our code was executed, which was not, which if condition works, and which not. So in this case, if the compiler knows it in advance, then we can fix some issues with branch mispredictions and so on. We may also know some additional information about trip counts and avoid vectorization of functions with a low trip counts and so on. So the idea is to collect some data while running our application and then to recompile the code. And here is how it is implemented. So now it is a 3-step process to use a PGO, which is profile-guided optimization. So first you need to compile your code with special profgen option, which instrument your executable file. After that, you just need to execute it and collect a dynamic profile information. And after that, on the final step, you may just recompile your code using this collected profile, and then the compiler will be able to apply even more optimizations to your code. Note that with the latest version of the compiler, we also introduced a profile-guided optimization based on vTune sampling, hardware event-based sampling. In this case, it's even more lightweight, so it's not actually instrumenting the executable code. Please refer to our documentation for more details on this feature. And the last but not least feature of Intel compiler is called auto-parallelization. So before we talked about auto-vectorization and data level parallelism, but I promised that we will talk about task level parallelism. So Intel compiler also supports OpenMP as far as you know, and it also supports auto-parallelization, which means by using a special option which is parallel, you may say to a compiler to try to automatically translate loops into equivalent multi-threaded code. So a compiler will go through your code, will try to identify the loops which are safe to auto-parallelize, which means, for example, there shouldn't be a data dependency, right? Right after read dependency in comparison with vectorization is now critical, and these kind of loops cannot be automatically parallelized. And if you want to get optimization report from the compiler, you can still do it by using qopt report phase par. In this case, you will understand which loops were actually parallelized using OpenMP and which were not. So underneath, the compiler is implementing auto-parallelization with OpenMP statements. And if you will enable opt report phase par option, you will see actually even the OpenMP directives which were used. So as you can see, we do have many different optimization available in our compiler. It is high-level optimization, it is auto-vectorization, which is one of the most important and powerful part, as well as inter-procedural optimization, IPO, PGO, and auto-parallelization. And in order to check what the compiler actually did, you can always invoke the optimization report and double-check what was done by the compiler and where you can spend more efforts in order to vectorize or parallelize the loop and get even better performance. So,
okay, Igor, thank you for your presentation today. We have more time and several questions have come in, so let's wrap up this session by answering some of them. Let's see, let's go with this question first. Question is, I want to have one version of loop generated with AVX instructions and one with AVX 512. So on the Intel Xeon Scalable processors, or a Skylake, it will use AVX 512, and on the Intel Xeon version 3, also known as Haswell, it would be AVX 2. Is that possible to do?
yeah, it's a very good question. So, and the answer is yes, it is possible to do it. Today we talked about -X options, which allows you to generate only one code path. So in this case, you can only generate AVX or AVX 512. But there is a different option, which is -AX, and it is a very nice feature of Intel compiler which allows you to generate multiple code paths, which means that you can target both AVX and AVX512 in one binary. However, it will increase the binary size of codes, but it will give you a better compatibility with different processors. So you can get even better performance. On Skylake, you will use AVX512, and on Haswell, it will use AVX. So yes, it is possible, and it can be done with -AX option.
Great. Another question came in. Why can't the compiler simply generate vectorized and non-vectorized version for any loop and choose a correct one in runtime?
It actually can do it, but the problem is that it's always a trade-off between the performance gain you are getting and an overhead which is caused by doing this. So theoretically, the compiler can do it for all loops, right? But finally, if there are many pointers used inside the loops, then the compiler needs to check that these pointers are not aliasing. And more pointers we have, the higher the overhead, which means finally we are not getting a benefit from vectorization itself. That's why by default the compiler is quite limited in usage with runtime check. So that is the question, the answer to this question.
Okay, another question for you. Regarding profile-guided optimizations, or PGO, what happens if the code of my application depends on input data?
Yeah, so since PGO is actually using the dynamic profile and the dynamic information of running your application, then of course it depends on the input data you are using. So if you use a specific set of input data and you compile your code and then run the application with this specific input data and then recompile using a compiler option again, then of course the compiler will optimize your code based on this input data and based on the code paths which were executed with this input data. So it's a user responsibility to understand how this works and to care that, that depending on the input data, the code flow doesn't change significantly. However, there is also a feature of a compiler, so you can use different input data and run the application 2 or 3 times and collect different profiles and finally merge these profiles all together. But once again, if the execution is dramatically different depending on the input data, then finally you will not gain a high benefit in performance. So
all right. Are you finished?
Yeah.
Okay, great. So there were different ways to help the compiler vectorize the loop with possible data dependency. For instance, compiler option, restrict keyword, pragma, IVDEP. However, all suggested options are compiler dependent. What is the best way to vectorize?
Yeah, right. So at this moment, there are different ways to help the compiler, but it depends on what you which way to vectorize the code you finally prefer. So if you are going to use the assisted vectorization and it works for you fine, then you are free to use all these options like f-argument option or pragma if-dep or restrict keyword. However, it is specific to a compiler implementation. So if you want to use an explicit vectorization model, then we would recommend to use OpenMP as a standard. So since it is a standard, it is supposed to be supported by all compilers. So in this case, using OpenMP pragmas to force vectorization and control vectorization, it is the best option for you. But you need to be careful, because in this case, a user should care about the correctness of the code and recognizing all the patterns of the code and so on. So if assisted vectorization works to you fine, then you can still use compiler Intel-specific pragmas like pragma ifdep or pragma always, and it should work fine.
Great. Another question. For vectorization, it sounds like it is better to avoid usage of pointers or structures or classes. Does it mean that we don't need to use object-oriented programming for performance?
Yeah, so it's partially true. So usually when you are using object-oriented programming, the final performance may be a bit less than you can get while avoiding it. But with the latest version of Intel compilers and the tools available there, you can still preserve the object-oriented style while getting quite good performance. So let's talk, for example, about structure of arrays and array of structures. So as far as you know, a structure of arrays is much more better, because there you can use a unit stride access. So let's imagine that we have one structure, and there we have array X, Y, and Z. So while operating with elements of each of these arrays, we can apply vectorization with no issues. But in object-oriented style, we usually introduce a class or a structure, and we have a field in this structure like X, Y, and Z, which means if we create an array of these structures, then we are accessing this data in non-uniform way, so not unit stride. In this case, the loop operating with it cannot be vectorized due to efficiency problems. However, with starting, I think, from 16 or 15 version of Intel compiler, we do have a nice library which is called SDLT, and it allows you to keep the object-oriented style of programming, but get a performance, because underneath it is changing the layout of memory to be unit stride. So the answer is yes and no, but with the latest features and libraries from Intel, you can even preserve your object-oriented style and get a best performance out of it.
All right, and the last question we'll take today is, does auto-parallelization work with more complicated patterns than a simple for loop, for example, for reduction?
So yes, let's say if there will be a reduction inside the loop, then once again it always depends on the code itself, on each specific loop. But in general, it works with reductions, so it is supported, and the compiler may auto-parallelize it. And in the optimization report, you will see that it's applied a reduction clause and first private to avoid data races and so on. So yes, it can do it.
All right. Okay. Well, that is all the time we have. Thank you, Igor, for today's Intel Compilers Overview presentation, and thank you to everyone for joining us. Please explore the Tec-Decoded website for more information on Intel performance and other useful and powerful Intel software tools, including how-to videos, articles, download links to the Intel compiler tool Igor reviewed today, and other resources to help you. Thanks again to all of you for joining us today, and we hope to see you again.